All right, hi everyone, we'll get started. So welcome. This will be the final review before your final tomorrow at 8 a.m. If you're here today or right now, you'll listen, and then it's also being recorded. So if you need to listen back to this at any point, you can reference it. So that'll be posted right after this is done. And then again, as a reminder, 8 a.m. in the same room that you take lecture in, so CHEM 113, or not CHEM, but I don't CB 113. You will be there for your final 2 hours, 40 multiple choice questions. I think that's the main things. Alrighty, so I will get started. You can ask anything that you want today, past exams, past quizzes, mock exam, general topics. You can use the chat, take yourself off mute, whatever's easiest. And then the next hour is yours. Anything specific that we would like to see?
Could you go over that one question on the mock final? It was like, I think it was like, the density one.
Yes. Let me Control F my mock final. This one.
Yes.
Okay. So we have an automobile antifreeze is made by mixing equal volumes of ethylene glycol and water. And at 20 degrees Celsius, the density of the resulting solution is 1.070 grams per milliliter. What is the mass percent of ethylene glycol in antifreeze? Alrighty. So can someone tell me how we would start this question? What is the first thing we're going to have to do?
Set up the equation of mass percent, so it'd be mass of solute over mass of solution.
Perfect. Okay, and how does that help us? Where do we go to from here? All right, we're looking for the mass percent of ethylene glycol. So is that going to be our solute or solution?
It will be our solute.
Yep, so this is going to be our ethylene glycol. Perfect. So how are we going to get to mass solute and mass solution? How is that going to help us? Or where can we go to from here?
What I originally did was say that density is equal to mass per unit volume. So mass would equal to density times volume.
Okay, so we know that we know that density is equal to mass over volume. So we know that mass is going to be equal to density times volume. Okay, so where do we go to from here? All right, we are not given a volume, but does that really matter in this case?
No.
Nope. Right, you can assume 1 liter if you wanted to. And then that kind of makes it easy from there. Right, so we can assume 1 liter, right? If you're not given a volume, but you need it, just always assume 1 liter. And that makes life kind of easy. Okay, so we know that mass is equal to density times volume. And we know that, right, we can then plug in mass for mass of solute. So in this case, if we have 1 liter or 1 milliliter in that case, right? Because then that makes it even easier. Then we could just assume that whatever our mass is equal to our density. So our mass of solute, we know ethylene glycol's density is 1.114, right? That would mean that we have 1.114 grams of ethylene glycol. Does that make sense? Okay, so once you had mass times density, or mass is equal to density times volume, what did you do from there? How does then that help us?
So the mass solute would be 1.114 grams, and it'll be divided by, so since we have 1 milliliter, since it's just equal volumes for ethylene glycol and water, the water mass would be 1 gram, and so the total mass is going to be 1 plus that the mass of ethylene glycol. So the mass of solution is just that value, 2.114. So it'd just be 1.114 divided by 2.114 multiplied by 100 to get the percentage.
Perfect, right? So we know that mass is equal to density times volume. We're assuming 1 milliliter. So we know that for ethylene glycol, we know that our mass is going to be 1.114 equal, or we know our mass is equal to 1.114 grams per milliliter times 1 milliliter. So we have 1.114 grams. That plugs into our mass of solute. So this is 1.114 grams. Our mass of solution is ethylene glycol plus water. We do the same math for water as we did ethylene glycol, so that's going to be 1.114 plus 1. So we have 114 over 2.114. And then we're going to multiply this by 100 to get 2%. So what did we get for an answer when we do that? About 52.7%.
Yep.
Yep, so that should be B here. Right, you end up with 0.5269. So that'll go to 52.7%. Okay, does that help the question on whoever asked that? Any other questions on density here and how we were using density in order to get to mass? Okay, make sure that like on your exam as well, you're kind of just looking for a roadmap, right? Your units are a really good roadmap. You know, you have mass and you can get the mass from a density. So then you're like, okay, where's my volume? If you're not given a volume, you can usually assume 1 liter, 1 milliliter, whatever's going to be easiest for that question. So then you would be able to see how much mass you can get to there. I believe, so someone asked if we were given volume, would we need to use the molar masses that it gave us? If you were given a volume, then you know how much mass is being added, right? If you said 10 milliliters of ethylene glycol was added with 50 milliliters of water, then you know, instead of multiplying by assuming 1 milliliter to get our mass, you know that you have 10 milliliters. So that's 10 times whatever the density is to get that mass there. So it's just going to change the amount of volume or the amount of mass based on the amount of volume that you have. So then you can get the masses from there depending on how much volume was used for both of them. If you were asked for, let's say, molality, where you needed moles of solute over kilograms of solution, that's when you would probably need the molar masses given. I think the molar masses given there are just because it's a question in chemistry and we always give you the molar mass kind of thing. Okay, any other questions on this density one here or question 37 on my particular mock exam? Okay. So in the chat, let me see. Someone asked for question 13 on the mock PDF. I just don't know what number that is or what question that is. I'm just gonna look that up. Okay, perfect. That was this one. Okay, perfect. Okay. What else is going on? Okay, so stuff from the beginning of the year about intermolecular forces. So when we look at intermolecular forces, what we just really need to know is solubility of these and like dissolves likes. Okay, so when we look at this, we need to know that polar molecules dissolve polar molecules. Right, so that's like polar dissolving like another polar compound. In this case, that would be like H2O and NaCl, right? NaCl is an ionic compound that is so polar, the electrons are transferred to the other nonmetal or to the metal in this case. And then H2O we know is polar because of its Lewis structure, right? So water's polar, that would be polar. Looking at two covalent compounds, if we had NH3 is a polar compound, and this would be dissolved in water here, right? Because this is polar as well. Likes will dissolve likes, right? In something non-polar, right? Carbon dioxide is non-polar, and that would be dissolved in something like butane. Right, these are all going to be, these are non-polar, the butane, and then the carbon dioxide is non-polar, so that would also dissolve in a non-polar and a non-polar. Okay. We need to establish our polarity first because, right, there's one question where we're asked for which one's going to be most soluble in the other one. You're looking for longer chains. So if you have something like an alcohol as methanol here, this has a short non-polar portion and it has a polar portion that can also hydrogen bond, right? So the shorter it is, then now your polarity is going to take over. This would be a polar molecule. This would dissolve in something like water. If we have something like butanol, now in this case, we still have a polar portion that can hydrogen bond, but now we have 4 molecules that are nonpolar, right? A carbon attached to a carbon, attached to a carbon, attached to a carbon. All of those are going to be nonpolar. The longer this chain is, the more nonpolar the molecule gets. If you just have one portion that's polar, but then multiple portions that are nonpolar, right? You have a skew here where it's like methanol, where you have your oxygen and your carbon. And as the carbon chain gets longer, they start equaling out, and then the nonpolar takes over. So you're looking for things that have a long chain to make them nonpolar, or you're looking for things that are symmetrical in order to make them nonpolar, and everything like that. The most important thing to remember when looking at these, if you can't draw out your Lewis structure, is that, right, always think back to what nitrogen and hydrogen, or nitrogen and oxygen look like when bonded to hydrogen. Nitrogen likes 3 bonds, oxygen likes 2 bonds. So this shape of oxygen here is still in the same shape as water. It just has now a long polar, non-polar chain instead of that other hydrogen, right? This still is the same bent shape that we know and love, but now it just has a long non-polar chain on the other side. Same thing for like nitrogen. Nitrogen likes 3 bonds. So sometimes there are 2 hydrogens and then a long carbon chain afterwards. That's going to make it more nonpolar. So that's really the big things you need to know about for intermolecular forces. And that's just reminding yourself of what does the structure look like, electronegativity differences, and how does that play into things dissolving in each other based on polarity. I don't think so. I don't think so. I think we asked you enough of that on like quizzes and exams in the first half of the semester. But right, your hydrogen bond is your strongest in terms of like the covalent compounds or covalent bonding. H bond is strongest, and then dipole-dipole. Right? Hydrogen bond is a dipole-dipole interaction that's just like a little elevated, is stronger than a dipole-dipole interaction. Right, and then LDFs are your weakest. Okay, any other questions on intermolecular forces? And to whoever asked that, does that answer your question there? Great. Okay. Is there any specifics about electrochemical cells or electrolytic galvanic? I think the big thing here is that if we have a galvanic or voltaic, what does that mean for E cell? What's the sign of E cell for a galvanic or voltaic cell?
Positive.
Yep, so this will be positive. And if E cell is positive, what does that make delta G?
Negative.
That's also negative. Yep. And so what does that mean for K? Is that going to be big or small? Good. K will be big. Right. So that's something to remember about galvanic or voltaic, right? And electrolytic is electrolytic. We know that E cell is going to be negative, which means that delta G is going to be positive, and which means that K is small. Okay, so if you remember just a galvanic or voltaic cell, if you don't see one of those, then you know it's opposite, right? But the big thing here is that your E cell for a galvanic or voltaic is always going to be positive, but an electrolytic, you have to put something outside. It needs an outside moving force. So your E cell will be negative when you set it up, cathode minus anode. Okay. What is this one? Okay. All right, can we do one of those buffer problems where you get to the initial pH and once you calculate? Yes. Yep. Okay. Okay, I'm gonna do the experiment 3 one first. Just because there's a question like related to that. All right, so when you do experiment or when you do question 13 here or looking at the experiment, right now we're saying how long will it take for the concentration of A to decrease to 0.175 molar in experiment 3? So the first thing you need to do is you need to establish what the order of your reactions are or your reactants are. So when we look at B here, going from experiment 1 to 2, we see that when we multiply, right, what is that, 0.5 by 0.5, 1.5, we see times 1 in our rate, right? So no matter what you change B by, the rate of B is, or the rate of those change is not changing. So if a concentration is changing, but the rate is not changing, that means that B is going to be 0th order, right? It is not concentration dependent, and so we don't need to worry about it. Which means that anything that's happening to A in the rate of A is going to be reflected, or the rate change is going to be reflected off of the change in A. So if we look at experiment 2 to 3, right, we'll have 0.350 over 0.250. This is all to an x power because we don't know what the rate is, or we don't know what the order is. And 0.525 times 10 to the negative 4 over 3.75 times 10 to the negative 4. So this would be 1.4 to the x is equal to 1.4. So what does x need to be in order to make that equal? X has to equal 1. So we know that A is first order. Right, that's just a setup because that doesn't even answer your question yet, right? That just sets you up because we're saying how long will it take for the concentration of A to decrease to 0.175 molar in experiment 3. So in experiment 3, we start with 0.350 and we're given 0.175 molar. This is just a half-life, right? This is taking 0.350 and dividing by 2. So there's 2 ways that you can do this. You can either, so now that you know that it's first order, you can say that the ln of 0.175 is equal to K times T plus the ln of 0.350, right? So then you can solve, right? You don't know what T is because you don't know how long it's going to take. But we do know that in T1/2, so you have to solve for K first. So T1/2 is ln of 2 divided by K. We know that we are able to solve for K because, right, we don't have K yet either, but we're able to solve for K because we have rate is equal to K times the concentration of A in our rate law based off of the fact that A is first order, right? We can use that example there. So you can plug in 0.35. This is very messy. I'm very apologetic. Right, you can plug in this into here. So you'll have 5.25 times 10 to the negative 4 equal to K times 0.350, right? And you can get your value for K. You can solve for it that way and then plug in this K into either this K or this K, and you can solve with either equation, right? If you recognize that this is a half-life, you can use the T1/2. If you don't recognize that it's a half-life, then you can use the integrated rate law for first order. If you're given a concentration that is not a clear half-life, right, then you only can use the first equation. So if you were given 0.1, right, how long does it take to go from 0.35 to 0.1? then you can just use this equation here. Grant, did I answer your question or did I confuse you more? Yep, of course. Okay. Okay, and then Charles, are you asking like the question from exam 3? What was that? Question 10 or 11? Yeah. Okay, so we can do something. It'll be pretty similar to the exam question. We'll just solve for a different pH. Okay. So the big thing that you need to start with here is that we have Ka2, 6.3, 8, Ka3 is, okay. So the big thing that we need to start with here is that we're given a buffer that has KH2PO4 and K2HPO4. So we're saying that we have, right, that's an ionic compound that'll dissociate in solution. We'll have H2PO4 and HPO4, which means that if we have H2BO4 as our starting reactant, which means that we are with Ka2. So when we're looking at setting up our buffer situation, right, we're given that it's a buffer, we need to identify which K we're working with. Since it's the H2PO4, that's K2, because the K1 would be H3PO4, and then K3 would be HPO4. So if we look at a buffer, if we recognize that this is a weak acid, weak base, we have to look at our Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of base over acid. And we're given the fact that the pH right now of the solution is 7.10. So we know pH here. We can get the pKa because we're given the Ka of either one of them, but we don't know our ratio of base to acid. So we can find that ratio. We know that our pH is 7.1. The pKa, if you take the pKa of 6 of Ka2, is going to be 7.20, right? If you take the negative log of that. And that's going to be the log of base over acid. So then you can get 0.10, negative 0.10 is equal to the log of base over acid. And we can see that this would be 10 to the negative 0.10 is equal to base over acid. So we know that the base concentration, right, again, these are all in concentrations, is the acid concentration times 0.794. Okay. What's important to ask yourself here, right, along these types of questions is this making sense? Does this make sense? If we're looking at your pH to your pKa, your pH is lower than or more acidic than your pKa, which means that you should have more acid than your base in your buffer at its current spot. Your base concentration is taking the acid concentration and multiplying it by something smaller than 1. So you should have lower base than acid. So right now we're set up correctly where we are in a spot where we have less acid, we have less base than acid, and we know the ratios of acid to base, right? So you give, even if you gave it so that you had 1 molar, right? Then you could find you had 1 molar of acid and then 0.794 molar of base. Okay, so that starts off there. That's your initial before you even add any acid. You are now adding HCl to your solution. HCl is a strong acid, which means that your pH should get lower. You are making it more acidic, and we get down to 6.9 pH. Okay, so once we know that, we need to then ask, okay, if I'm adding acid, is this going to react with my base or my acid of my buffer solution? You are adding acid, so you're going to react with your base. So if you're looking at something where you have a ice table, right, you're adding acid, your initial is say 1 and 0.794, right? You're adding acid, which means you're adding to this side, right? You're putting acid in solution. So it will react with, I guess you're adding acid, or you're adding acid to this side, it'll react with your base, and so you'll subtract from your base component, but you'll add to your acid component, right? You're going to make more acid in solution, so you're using up some of the base that it is reacting with from the addition of acid and creating more acid, creating more of that conjugate acid or that weak acid you started with. Right, so once we know that, then we can say, okay, I know that I have the same change in X for both of these. So now my new Henderson-Hasselbalch equation is 7.20 plus the log of base over acid. But now this time, right, we have negative 0.30 is equal to the log of your base was your acid times 0.794 minus X over your acid plus X. Okay, does that make sense? Your acid, we said from our question, was 0.1 molar. So we can plug that into our solution or into our equation. And then 10 to the negative. Right, so now you have this ratio of your acid to base and your new 10 to the power of negative 0.30. And then you can just solve for x that way. X here would be the number of moles directly added because you don't have any change in volume. And so that's just going to directly be the moles. Kareem, it was given to us in our question. So we said that the KH or KH2PO4 is equal to 0.1 molar. So this, right, this is your acid concentration here. This acid concentration is, right, this is 0.100 molar from question. I didn't do it fully, but that would make sense based off of, right, you added 0.01 from your exam to drop it by 0.1, so to drop it by 0.2, I would guess you'd add 0.02 molar, or 0.02 moles. If you don't have 1 liter volume, then all of this is given to you in concentration, right? This is a concentration of 0.1 molar. So then you just have to convert everything to moles by multiplying by the molarity by the volume. And then at the very end, you would be getting a concentration of X that's changing. And you want to multiply that by the total volume. Yep. So I guess I'll just follow this through. Right, if we had 0.501. So I got 0.0195 molar, right, that we're changing. If this was a change in volume, right, this is moles over liter. Since we only have 1 liter, there's no change in volume. If we multiply by 1 liter, then we get 0.020 moles of acid that's being added, right? However, if we had a change in volume, let's say to 1.1 liters, and then it would be 0.0195 molar times 1.1 liters. So you would get 0.021 moles. Does that help your question, Charles? And did everyone understand why we were multiplying by 0.1, where that concentration came from? Yes, yep. So you would start off with something that was 1 liter. So your original pH calculation, right? This chunk here, that would stay the same. But when you get down to this portion here, all of that should probably be in moles first. But I wouldn't worry too much about that. I think if we were to ask you for volume change, we would ask the question slightly different. So you knew to get to the moles first. They would ask you how many moles are being added kind of thing. So you have a concentration and volume to begin with, and you can get the moles directly. Perfect. Okay. And everyone saw why we were multiplying by 0.1. Are there any more questions on where that concentration came from? Um, Okay, so for question 18. Right, in chem labs, students use ammonium buffer during the EDTA titration experiment to facilitate metal binding to EDTA, which of the following pairs of solutions would form the most effective ammonia buffer when mixed. All right, so you're looking, the big thing to recognize with ammonia or with buffers, period, is that you want a weak base and a weak conjugate acid, or a weak acid and weak conjugate base. Okay, so you're looking for that combination, like at the end, once you've combined things. In this case, we're looking for an ammonia buffer, which means that we want the situation where we have a weak base and a weak conjugate acid set up. And we want, like if we're thinking about an ice table, we want ammonia on the left side of our ice table. Okay, so when we're looking at your various questions or various options here, we are given ammonium, which is a weak acid, and we're given HCl, which is a strong acid. The first thing you need is you need opposite types, right? So when we have a weak acid and a strong acid, that's two acids, that's like two positive parts of a magnet. They're not going to do well together. They're not going to make a buffer. Automatically get rid of that kind of option. We then have a weak acid and we have a strong base in this case. That can be a situation, right, depending on which one is in excess. In this case, your weak acid is in excess. Okay, so that it has potential to be our solution, but we'll see if there's better options. In this case, we have a weak base or a strong acid. That's better because your base is the weak portion, right? We want an ammonia buffer, not an ammonium buffer. So your ammonia being your weak base, that is in excess. Or wait, not in excess, right? Your weak base is first, that's more towards our ammonia buffer scenario. But weak base and strong acid are equal. Right? They have the same number of moles of the weak acid, of the weak base and the strong acid. So this puts us directly at the equivalence point. Right? We're directly at the equivalence point, and so that's not going to create a good buffer because we want to be in that buffer range where we have excess weak component when we're trying to set up a buffer. So then let's look at, so I would say C can be eliminated. And then when we look at choice D, we have our weak base and we have our strong acid, but this time your weak base is in excess. And so since our weak base is in excess and we're looking for the weak base component to be our buffer, D is our best choice because we want an ammonia buffer and we want our weak base to be in solution. Additionally, right, the higher concentration allows for more ions to be in solution, and that'll grab the addition of acid or base a little bit better than a weaker or lower concentration. So D is going to be your best choice there. Any questions on that one?
I have a question. If the question was asking for the most effective ammonium buffer, would it have been B?
Then it would be B. Yep.
Okay. So do you think it's important to recognize NH3 and NH4 as which are acid and which are base for the test? And like
Yes, but additionally, you have ammonium given to you in your question, and she writes it as, right, ammonium, and then base acid, right, NH3 and NH4 plus.
okay, got it.
And then anything with the nitrogen is almost always a a base. So if you just have nitrogen and 3 things attached to it, most likely going to be a base. And then when it has that charge of the plus, that's when it becomes an acid. So if you just look at those differently and look at like, what does it mean to be an Arrhenius base and acid, right? Proton donor, proton acceptor, then it would, then that might trigger some clues to which one's the acid, which one's the base as well. One asked, could you show the reaction of how the NH3 first reacts with CCl and then forms a buffer? So, sorry, my internet connection just died for a second. That was so weird. Okay. Zoom. Share screen. Oh. Okay, sorry. So, right, we have NH3 and HCl, 50 mils and of 2 molar and 50 mils and 1 molar. So when we first tried to introduce chemical reactions to y'all, right, you would say, okay, what are the predicted products? You would say it was NH4 plus and Cl minus. And then because I gave you a concentration and a volume for both of them, that should trigger a limiting reactant question for both of you, or for this type of question. So you could solve for the number of moles by getting your concentration by volume, and you would see that HCl is your limiting reagent. Okay. You could then say how much is left over. What is left over is this guy here, and that's NH3 at now, right, half of its concentration, right? So now NH3 is just left in solution. We have no HCl, we have NH4 plus and Cl minus. So now this NH3, right, and these are not contributing to the pH, right? The pH is dictated by H plus ions and HO minus ions. So those are not contributing to anything in the pH, they're just there. So now for NH3 will then say, okay, I've now formed I've now reacted with the base in solution, but it's aqueous, so I know that water is around me. So now I'm going to do my acid-base reaction that I know, and whatever is left over of that NH3 is going to have an acid-base reaction type deal situation, right? It's like, okay, I've done my job with my acid, and now I can just do a normal dissociation with water. So this is what is left over, and this is what creates the buffer because we have excess base that did not react with our acid. Any other questions on 18? Does that help my person that asked about that one? Yes. Okay. Katie, are you talking about this one here?
Yes.
So when we look at standard Gibbs free energy for an electrolytic cell, right, the important thing to note here is that E naught cell is negative. Okay. So when you set up your E naught cell, when you do E naught cathode minus E naught anode, right? You want to make it and look at your values here so that it comes out to be a negative value because you're in an electrolytic cell, it should be negative. So when we're looking at our values, we see that we have a negative 1.16 and a positive. So we'll take E naught cell, and to make it the most negative, it'll be negative 1.16 minus 1.066. If we did it opposite, then we would get a positive 2.226. But in this case, we get a negative 2.226. Okay,
Would
we want to, go ahead.
Sorry, would you have to multiply it by 2 to cancel out the electrons for that other equation?
If you needed to balance it, then yes. However, if we're just solving for delta G, right, you just need to say, okay, what's my E naught cell first, and then you need to figure out how many electrons, like when you actually use the delta G equation. Even if you're multiplying your reaction by 2 to make the electrons equal, that doesn't change the number of volts of your reaction. Does that make sense?
Yes, thank you.
Yep, right. So even when because eventually we'll need to do, we'll eventually need to balance our equation or electrons to see how many are being transferred. So this would still be 4Br2, 4E minus goes to 4Br minus, but E naught of this cell is still 1.066. Okay, so once we have E naught of the cell, then we know that delta G naught is equal to negative NF NFE naught cell. So, right, we said we had 4 electrons here. We made this 4 electrons here. So this will be negative 4 times Faraday's constant, 96485, and then negative 2.226. So then delta G becomes 859 kilojoules per mole. What is my trait? So I think I'm doing least common multiple as much as possible. So, right, we're looking at 4e for our one equation, and I'm looking at 2e for our other equation. I know at some point I'm going to have to add them up, so I need to make those equal. It's given to you as balanced redox reactions, so you just need to make sure that those are equal. So, right, how do I match my lower number to my higher number? So, right, in this case, that's just multiplying the second one by 2. When you have 2 and 3, right, the least common multiple there is going to be 6. So I just look for that pretty easily. And I think I'm just doing least common multiple in my head. We're seeing like, okay, how do I make these match? And what do I need to multiply to get them to match? And if they're given balance, then you can just multiply that and it should work out. More of like a puzzle as much as possible. All right, Katie, does that answer your question on this one?
Yes, thank you.
Yep, absolutely. Okay, and then the delta H, let me just look. So when you're looking at this question here, consider the dissolution of sodium nitrate into aqueous ions of water, right? We're talking about that lattice of hydration. So we know that ions dissolving always increases entropy, right? It always increases the amount of disorder to have a solution over a pure solvent, right? So if you have solid and if you have something aqueous, that will always increase delta S, or always increase the entropy or disorder of the solution. So when you're looking at this type of problem, right, we can automatically get rid of sorry, you can't automatically get rid of anything like that. But when you're looking at dissolving something, right, that's always increasing entropy no matter what. It's always increasing entropy. However, the process of getting to increasing entropy depends on the delta H of everything else going on. So, right, this goes back to, the slides where it gives you like, it goes up like this, right? You have like stepwise, and you have lines here. And then it's like this. If it ends here, then this is endothermic. Or if it's like this, then it's exothermic. I don't remember what chapter that's from, but I can see the slides in my head. But it's just relating to these two. So if the delta H of your hydration is harder to do than the entropy of the solution, then you will have a cool solution afterwards, because the change in entropy is not enough to make up for the change in enthalpy that you're getting for dissolving something. So if you have something cool, that means that your delta H or your delta S change is not big enough to overcome everything else, which means that your delta H of solution would be less than 0 because it's not coming up enough with your delta H. Also to this matter, the lattice energy, in order to overcome the lattice, is too high in order to have the solutions, or in order to have the ions dissolving and releasing that energy from the bonds that it's making with its water and everything else. If that lattice is too big, then you have a lower delta S as well, or you have a lower delta H, or you have a cool endothermic reaction. So because of the fact that we have a spontaneous at room temperature but lower temperatures, the solubility of sodium hydration decreases, right? We're saying that the cooler everything gets, the less soluble the reaction is, which means that your lattice does not have enough energy to overcome it, right? You don't have enough heat to overcome the lattice energy required to break those bonds in order to dissolve those bonds. Yes, so I had a couple questions come in right there. Sorry. Is the lattice the bonds breaking, and if this reaction endothermic, bonds are forming and the lattice is less than 0? Yes. So to clarify, lattice is breaking bonds and hydration is forming. Yes. Yep. Lattice is the energy to break them because it's already in, right? Like it's rectangle. So you have to break those lattice. That's going to require energy. Then it's going to reform and dissolve into its ions, and it's going to interact with the water molecules. That's like forming bonds or forming intermolecular forces with the solution. So that is going to be hydration is bonds forming, lattice is bonds breaking. I might have picked the wrong one then. Sorry. Yeah, your delta H of the solution, sorry. Your delta S should be greater than 0 because entropy is increasing. Yes, so if it's endothermic, that means that there is not enough energy to, right, it requires more energy for the lattice than it does for the bonds forming. Charles, that's a great point as well, right? You can say that since it's also endothermic, then both S and H are positive, and you can go from there. That's absolutely true. Yep. You cannot assume delta H lattice is opposite of delta S, because you could have an enthalpy that is exothermic that's increasing heat, while also have a delta S that is increasing, so positive. But you can have an endothermic reaction where delta H is positive and then delta S is also positive because you're increasing entropy. So you can't assume that, Kareem. Yeah, so someone said, are there mental checkpoints we could use when looking at a question like this? Like first you could see what reaction is occurring, then try to decide if it's endo or exo. Yes, for sure. Right, you want to look for things that are cooler to the touch, or want to look at things, right, hot to the touch. What happens there? If it's cool, it's endo. If it's hot, it's exo, because cool is taking in energy, exo is releasing energy. Right, the reaction or the process is spontaneous at room temperature, but at lower temperatures, the solubility of the sodium nitrate decreases, right? Then we're saying that, where is that looking at delta G? What are my signs of delta H and delta S? What's happening there? Right, if we have delta G is equal to delta H minus T delta S, right? If this is spontaneous at lower temperatures, what does that mean? That means that the lower this gets, right, the lower delta T becomes, this is positive, right? This is negative, kind of stuff like that, right? How does that change? How do your delta H's and delta S change depending on what's going on or what's occurring spontaneously? And then how does that change in terms of what does it mean for lattice and hydration kind of thing. Kinsey, do you remember what question it was on exam 1? I can try and pull that up real quick. Question 9, mock exam. Yes, so when you look at that question, that is telling you that, right, when an unknown compound MX dissolves in water, the solution feels cool to the touch, and which of the following pairs of inequalities is correct for this process? So because it's cool to the touch, right, that means it's endothermic. And if it's endothermic, that means that our lattice, or the energy required to break our lattice, is more or greater than the energy that releases when our ions that were broken in the lattice are now dissolved in solution, right? So you're looking for, okay, if it's cool to the touch, what does that mean about my lattice? That means that my delta H of the lattice has to be greater than the hydration of my ions, right? Because it is going to take more energy to break the ions apart than it is to dissolve them. And then if we're looking at delta H to delta S is increasing, but that will always be, but delta S will always be greater than the delta H of your solution in an endothermic reaction, because the dissolving of those ions will always create more entropy. And if it dissolves and it creates an endothermic reaction, it's still dissolving, and that is increasing more energy, or that is increasing more entropy to overcome the value of delta H. Right? The energy is overcome by the disorder that is happening or created with the dissolving of the ions. Does that help a little bit? I know that's kind of confusing, but I would look at those slides from whatever chapter that was. What was that? Like the 3rd unit we did, 2nd unit we did. If you can find the slides that look like this, right? Maybe just review those super quick, and then that might also make a little bit more sense besides me just rambling. Sorry. Or forget about it and just think that it's one question on a 40 multiple choice question and hope for the best. Get everything else right instead. Alrighty, I will end here. I'm sure you're tired of hearing me talk now as well. But I will post this recording in, before 3 o'clock probably. Once I get the Zoom recording back, and then good luck tomorrow. And I will see you bright and early. Set multiple alarms. Set it right now. If you don't have an alarm set it right now. And thank you so much for a great semester. It's been a pleasure being your IA, and I wish you the best of luck. And I will still be here if y'all need anything. So reach out if you ever have any questions, and I'll keep on top of my email as much as possible tonight as well. Thank you for a great summer or semester, and have a great summer. Bye, y'all. Thank you.